I have made many videos about sideband noise in oscillators, amplifiers and components, and they are up to number 116, and as you can see here. In this video I am doing something that is not only for nerds, I think more general interest, and that is how to measure noise generated by capacitors when using them in high-frequency circuits. The first requirement in a project like this is a good low-noise oscillator. I am using 10 MHz for everything. This oscillator is a 501 25420 from Wenzel Associates. The nominal power level is 13 ± 2 dBm into 50 ohms. To get the full performance in terms of sideband noise, it is necessary to isolate the unit from vibrations, from temperature fluctuations, fast temperature fluctuations, and particularly to have a very well filtered supply voltage. Here I have capacitors with a total of a bit above 3 farads, and there is a 5 ohm resistor in the DC supply line, and you can see there is a choke on it to avoid RF, and there is also a balloon here to avoid currents on the screen of the cable. And one more thing, it is important to tune, there is a tuning screw. It should be set fully clockwise, otherwise there is much more noise. Maybe I could adjust the frequency with the frequency control pin, but I haven't tried that, it is grounded. I'm using the Wenzel oscillator for two purposes. Firstly, as the test signal feeding it to the capacitor to be investigated, but also as the reference signal to the PN2060 analyzer. The signal comes first to this low noise amplifier, and then to a second amplifier, this one, and a third amplifier here, and then the output goes to this power divider, on which there is two 6 dB attenuators, low noise, and then a third 6 dB attenuator here on the way back to the PN2060. Here is the PN2060. This decoupling of the USB voltage was unnecessary. I did it and it turned out to make no difference. This box contains components that make the PN2060 see 50 ohms at high frequencies, because it is necessary to terminate it at frequencies generated from the ADC, which operates at 133 MHz and modulates the 10 MHz signal and sends back something. And not having it terminated properly destroys, or at least degrades, the performance of the PN2060. And then there are proper 10.7 MHz low-pass filters, because this box attenuates overtones, but not very much. But the combination removes 20 MHz and higher very efficiently. To evaluate the sideband noise of the device under test, here it contains the capacitor I am interested in. I am using this interferometer. The test signal with its 29 dBm is split into two equally strong signals. One goes through a stepped phase shifter containing cables of various lengths, differing by a factor of 2. And then there is a stepped attenuator which has a position for infinite attenuation when it is 50 ohms at both sides but doesn't allow any signal through. And then there is a continuous phase shifter which I have made with resistors and variable capacitors to avoid contact resistance noise. And it works beautifully. And then there is the device under test. And the other channel I have stepped attenuators, one coarse and one with fine stepping, and one with capacitors, variable, that allows a continuous fine tuning. I can set this with a precision so I can go down to minus 60 decibels of attenuation. But with the signal levels available, just 1 watt or a little bit less than that, I don't need very much attenuation. Then this hybrid takes the sum of these two and the difference. The sum signal goes to trigger the oscilloscope. The difference is the signal of interest, and it goes through a coupler and then to the signal analyzer. The coupler picks minus 9 dB of that signal, and then I have an attenuator and look at what comes through with the oscilloscope. So the procedure is to set this attenuator to infinite attenuation, means I will see the signal only this path. And then I set this one to the desired attenuation, for example 40 decibels, and look at the amplitude on the oscilloscope. Then I set this to 0 and tune the knobs here so I get the same signal level that I had when this was 40 decibels. Means now the carrier is 40 decibels weaker into the signal analyzer. So the phase noise generated by the device under test is not cancelled by this procedure, so it is now, in this example, 40 decibels stronger and easier to see. As a first experiment, I will skip this interferometer and measure the test signal directly by the correlation receiver. This is the receiver, the signal analyzer for correlation measurements. So it starts with a hybrid that splits the signal into two equal parts, and then an attenuator in each channel, and followed by low noise amplifiers, and then there are two couplers to send one signal this way into the Linrad 2-channel receiver as device under test 1 and device under test 2. And the other goes to amplifiers, followed by stepped attenuators and low-pass filters at 10.7 MHz on the PN2060, as you have seen already. The Linrad path starts with attenuator and an isolation amplifier and a low-pass filter on 15 MHz, because Linrad uses Schottky diode mixers, and I don't want the local oscillator from them to go back this way and get into the signal path of the other receiver, the PN2060. It could also be the SDR IPs that I have connected here. Here is the block diagram over the reference oscillators I'm using in Linrad and also in the PN2060 for channel 2 there. It all starts with a rubidium reference at 10 MHz, and then it is divided down to 24 Hz and 48 Hz. That gives me, with a flip-flop, two signals at 24 Hz that are phase shifted by 90 degrees. And then I take the 10 megahertz signal and shift it to 90 degrees and the signal direct. And then a quadrature mixer gives me 10.00244 megahertz. That signal is used for a PLL to the oscillators. Local oscillator number 1, buffer and couplers, and it goes to the lean rod SDR as the reference 1. And the other output is currently unused. I could use it for SDR IP. And then the other reference oscillator, LO number 2, it has a buffer and a coupler, and then there is an output to use it as the reference for the PN2060. And another coupler to use it for reference 2 for lean rod. At of course 10.00244 megahertz. And then the PLL is the same as here. First divide the frequency by 8 to get 1.2 megahertz. To having the PLL at the lower frequency means that the phases between the two signals can vary much more. It can turn many turns around before it loses locking. And that's good because I want the phases to be uncorrelated down to very low frequencies, well below 10 seconds. The LOs should be uncorrelated because I'm using these two oscillators to compute noise from a correlation procedure. And the rubidium oscillator is very noisy, and I want to suppress the noise from that down to well below 0.1 Hertz. After almost 1.5 hours and 775 averages, 776 now, I can see that the phase noise of my amplified Wenzel oscillator is at minus 120 dBc per Hertz. So amplifiers have not degraded it significantly. The amplitude noise is lower, about minus 129. And that is caused by the amplifiers. Here is the result I see in the PN2060. It is lower, it is below minus 130, and it has not converged. You can see all the slow circles telling me that it is not a valid result yet, although it is almost 1.5 hours. And the number of averages is only 105, so it will take a long time to see where the limit might be. The reason this is much better is that the same signal is used as the device under test and for the reference in channel 1 of the PN2060. That's why it shows that the frequency is 0. And it's okay for this test system, but since the signal is the same, there is no noise contribution because frequency variations in both inputs are identical, except for what is caused by various attenuators and other stuff I have. So this should be very low here. In channel 2, the noise from the signal source, as well as the noise from the channel 2 reference oscillator, is present. So that is at the same level that I saw in lean rod, minus 120 or so. But with correlation, that averages out to 0. So that doesn't contribute. So what I see is the noise from filters in front of the PN2060. Now, after 10 hours, the level I see is a little bit lower. It's about minus 138, and that's what is said here also, of course. Now, I don't know where the limit would be, but I do not want to have measuring times exceeding this. Winrad is of course still reporting minus 120 for the phase noise. I will now connect the interferometer to run the signal through this package, and the device under test is a 1 dB attenuator, because I have to compensate for some losses in this circuit here that are larger than the losses here when set to minimum attenuation. I will set the balance for a very weak carrier, 60 decibels of suppression, because then I will see the noise generated by these, or maybe the noise from the analyzing radio, because the carrier will be very weak. I will set these attenuators here and here to minimum to get the maximum signal into the analyzing receivers. I set this attenuator to 60 decibels, like that, and then I switch off the signal in one of the legs by setting this to Z0, so it has infinite attenuation. This is the signal level I want to send into the analyzing receiver, so now I switch over to have both legs connected. And of course the signal is much weaker. So I remove 20 decibels and turn the knobs. Here something. And finer tuning. Here is the phase correct. No, there. And it takes some time. Stop the video. Now attenuation here is 0, and I have the correct signal level, and I can fine-tune the phase now, and you can see how it behaves. The attenuation I had to set is 0.7 decibels, and I want to maximize the signals into the receivers. Zero. So, after 1 hour and 24 minutes, the phase noise reported by Winrad at 1 Hertz is minus 109. That means minus 169 dBc per Hertz. And the uncorrelated noise is significantly higher. The signal level is 40 decibels below the limit for this receiver, the saturation of the AD converters. And the carrier level has stayed at the proper level. The PN2060, the signal level is minus 27, while the maximum is plus 10, so it is 37 decibels below optimum. Here the noise is stronger. I can see at 1 Hertz about minus 92 or 91 perhaps. The cursor is a little bit high in relation to the noisiness here. There are no circles, so this is a real correlated signal coming from somewhere. Probably the front end of the PN2060 because of the very low signal level. I change the attenuator here to 50 decibels, like that, and then look at one leg only, and of course the signal is now stronger, So I put the markers for it. And then, like that. And now the signal is very weak, but I remove the attenuation. And then I have to bring up the signal. So I turn the controls, 0.1 decibel, that's too much. So I have to use the analog, and that changes the phase, so it interacts with the phase control here. I need both hands to do this adjustment. And now carrier suppression is 50 decibels. 4 hours at 50 decibels of carrier suppression has given me minus 117.5, or if I even out it says minus 118. Plus 50 means minus 168. That's the same result that I found at 60 decibels carrier suppression. That's interesting. Now, the amplitude noise, I forgot that at 60 decibels, but here we have it at 50. It says minus 102. And I have good reasons to believe it was the same also at 60 decibels. Because the difference between the correlated and the uncorrelated is very small. And attenuators, they give amplitude noise but not phase noise generally. And there are attenuators in the interferometer. The PN2060 has converged nicely at 1 Hz, showing minus 100.4, means minus 150.4. The advantage with the PN2060 is that it gives a much wider frequency range. So the structure I see here is because the signal level is very low, so mismatch at the input hybrid of the correlation system becomes critical. So what I see here is the noise of the termination resistor that comes because of mismatch at the hybrid. This is a well-known problem, and I just can discard what comes here. But I can trust results up to maybe 100 Hz offset. And the signal level here is minus 18.4, means 28 decibels below the maximum level for the PN2060. It's still a very weak signal. And in Linrad, the level is 31.5 dB below the point of saturation. Now carrier suppression is 40 decibels. The signal level I see in Linrad is 21.5 dB below the point of saturation. And the phase noise comes at minus 120. This is different from before. 120 plus 40, that is 160. I saw 168 before. The amplitude noise is minus 112.7, well, minus 113. The decimals are not certain enough, so I don't note that. The PN2060 has a signal level of minus 8 dBm. That's 18 dB below nominal power level. And the readout from the cursor is minus 113.5, but looking at the curve, it is more like 110.0. And the time is 1 hour and 50 minutes. Now the carrier suppression is 30 decibels, and then the level I see is 11.5 or maybe 12 decibels below ADC saturation. The phase noise is now minus 120, just as before. But this is the level of my test signal, because the sideband noise and the carrier are suppressed to the same extent. I am looking for the noise generated by the interferometer, but that is not visible. The amplitude noise is about minus 122. And the result I see with the PN2060 is minus 120. Now at 20 decibels of carrier suppression, the level I see in Leanrod is 1 dB below the point of saturation, or a little bit more than that. The time is 1 hour, 17 minutes, and what I see is of course the signal, the test signal at minus 120 in phase noise, and the amplitude noise is minus 129. For the PN2060 I had to add 2 decibels of attenuation to not give it too much signal. That gives a level of 9.5 dBm into the PN2060. And it has not converged quite yet, but I can see that the level is minus 130. And plus 20 means 150, as before. Here is what I found. With Leanrod, I can see phase noise down to, let's say, minus 160, with a margin to the unit noise floor of 8 decibels. That requires 50 decibels of carrier suppression. And the amplitude noise is 15 decibels stronger or so. The PN2060 shows the same result all the way, minus 150. And it is a little bit worse if I have no attenuation, but the difference is not large. And that's because I have this trick with the same signal as reference and as test signal. Whether this is really true, minus 160, or if there is some artifact that I'm not aware of, I don't know. The device under test now is this 2 dB attenuator from Applied Research. I know since before that this is noisy. The carrier suppression is 50 decibels and the phase noise at 1 Hz is minus 99 dBc per Hertz in Leanrod. That is in good agreement with the PN2060. It reports minus 98, but I can see the cursor is a little bit high. So phase noise minus 99, and then plus the carrier suppression, 50 decibels means minus 149. In Leanrod I can see the amplitude noise. It is 10 decibels stronger, minus 89 dBc per Hertz at 1 Hertz offset. I tried to measure the amplitude noise with the PN2060, but this does not work. The frequency is incorrect. Big numbers come out as the difference between the frequency of the reference and the device under test, and the curve is completely crazy. Now, the signal level is fairly low because I have this carrier suppression. The level is only minus 21 dBm. But phase noise works fine here, so something is bad with the algorithms for amplitude noise. And here is what I see. The impedance is 45 ohms and fairly close to resistive. So this is a good enough match. At 50 decibels of carrier suppression, the phase noise I see is minus 117. That doesn't differ significantly from the 118 that I saw with the 1 dB attenuator. So I don't see the phase noise from this LC resonator. The amplitude noise is minus 100. That differs by 2 decibels from what I saw, and that is not significant really. Means I don't see any problem with these capacitors with Linrad. And as I wait long enough, it goes back to the correct level. A very interesting thing now is that the noise is much better. I can see that already by looking here. And you can see here, the noise I had problem with, it's gone. I will reset Linrad and PN2060. Now the sideband noise is much lower. I read minus 100 dB now, means 150 dBc per hertz. And particularly look at the waterfall. All this noise has gone and the spectrum is black on the sides of the carrier. So these polystyrene capacitors have unstable connections. I have seen that before, but not with these particular ones. So I have to look at other capacitor types because I cannot use these Chinese polystyrene capacitors anymore. The signal level is stable now, close to the right value. I have not changed the controls for the interferometer. At 1 Hz, amplitude noise and phase noise have the same level, and further from the carrier at 2 Hz, the correlation is very strong, means AM noise and phase noise have the same origin physically within the device under test. And waterfall looks nice. I have replaced the polystyrene capacitors with this mica capacitor with a very similar capacitance. And I have retuned the coil very little, half a turn or something. There is a copper slug that can move inside to change the inductance. And I also tweaked the links on both sides of the coil to get the desired coupling. The impedance is very close to 50 ohms at the correct frequency, 29 Hz above 10 MHz, and the Q is 15.65 and the loss 5.8. The signal level is a little higher, 36.2 volts. This capacitor is useless for my purposes. The noise level is very high. It's about minus 80 dB in Linrad, in full agreement with the PN2060, which also gives minus 80. And you can see the waterfall. It has been noisy. Suddenly the noisiness has gone down, but it is not zero. I will reset the receivers. The noise is lower, but it still varies with time, and it's still too high. Minus 86 plus 50, that's not good enough. This is not what I want to use in an oscillator. These are modern silver mica capacitors, and I didn't have to tweak the coils. I just changed the tuning slug a little bit. And then this is what I see: 51 ohms, Q 15.3 and loss 5.2. The signal level is 37.6 volts. The noise level is ridiculously high. I read minus 75 dBc per hertz in Linrad as well as in the PN2060. That means minus 125 dBc per hertz because the carrier suppression is 50 decibels. And when I look at the amplitude noise, I find it's much weaker. After a while the noise has come down, but it's still not good enough. You can see the sharp event that happened, and then there is some noise coming back. These are ceramic microwave capacitors. one each of these ones. They make 269 pf. I had to change the tuning slug just a little to get the correct tuning of this resonator. Impedance 50 ohms, Q 15.5 and loss 5.4. The signal level on the capacitor is 36.8 volts peak to peak. This is nearly 5 hours. The phase noise is at minus 108, means minus 158 dBc per hertz. And of course the PN2060 tells me something differently, because it doesn't have that dynamic range. And the amplitude noise is a little bit stronger. It's at minus 101. And above 1 hertz, the correlation is weak. What we see here at very low frequencies are artifacts from the evaluation. Data is not valid below about 0.8 hertz. There is a problem with these capacitors, however. That's why I put the cloth above. I remove it. And of course I get a burst of noise while moving that, but we will wait for a while. Nothing special happens, not yet. But now I do like this. And that gives a clear problem in the lower waterfall, the close range waterfall. Very interesting. The unit has been running overnight. Yesterday, when doing this, waving me my hand above it, it went into a noisy state that lasted for maybe 3-4 minutes and fell off exponentially. But now it's not as bad. I changed the intensity scale of the waterfall here. The phenomenon is still here. It's in the close range, and you can see the green phase noise very close to the carrier. I don't want to start evaluating it because it will gradually fall off. I think the explanation is that when the capacitors change size because of the changed temperature, the cooling I do is very small, because it is the same air temperature, but there may be strain in the ceramics since I soldered it very recently. I will try some temperature cycling procedure to see if this becomes better. This lamp gives a lot of infrared radiation. The carrier suppression has changed. The carrier is a couple of dB stronger now. I'm not going to bother about that, because the noise has increased very much, so that small change of the carrier level has no significance. And it comes in steps. If you look at the spectrum here, one can see bursts of noise coming up and down, like that. The carrier is much stronger now. You can have a look like this. It is 2 steps, roughly. That's a factor of 5 in amplitude, 25 in level. So I switch off the lamp. I don't shake anything, just step on that foot switch. It's questionable if this is something to use. Seems it would have to sit inside the thermostat oven. I don't know. Means it would cycle in temperature a lot each time I switch on and off the unit. And then it would need several hours to stabilize, probably. The signal level is back, so the capacitance is restored now. The time is about 40 minutes and it's still very noisy. I will wait for it to stabilize and see if this repeats or not, and I try several times. Amplitude noise and phase noise are strongly correlated. There must be some strain releasing process going on in the ceramics. Whether it's a memory since I was soldering on it, or whether it is a problem with the small temperature adjustments I do with the light source, I don't know. This is when I enter the room after a little more than 1 hour. If I cause vibrations or cause a movement of air, I don't know, but I make this thing again. And you can see immediately strong sideband noise. I switch on the light again. That causes the carrier level to go up again. It was at the proper level before, so this is a temperature drift. The frequency drifts with temperature. The wider trace here is partly because the carrier is stronger, but when it comes these things, that is interference, noise pulses. I think it looks the same as previous time, and I don't think I will do any more with these capacitors. These are two series connected 560 PF ceramic capacitors in glass encapsulation. Impedance 50 ohms, 0.87 it says here, Q 12.9 and loss 6.92. I had to change tuning a little and also move the links a little bit to get these values. The signal on the capacitor is 29.2 volts peak to peak. This is significantly lower than before. These capacitors are a bit lossy. The phase noise is at about minus 100 dB, means minus 150 dBc per hertz. And the amplitude noise is similar. I can compare them, and as you see they differ by about 2 decibels. I don't have 270 PF polypropylene, but I have 470 and 680, and with them in series I come pretty close. After some retuning, I get 50 ohms and Q 15.2 with a loss of 5.4 dB. Across the capacitors I have 35.4 volts. I read minus 107.5 for the phase noise. Or maybe 107 plainly. And the amplitude noise is at minus 102, say. And if I compare, it's clear that the amplitude noise is much higher than the phase noise. 102 and 107. I made a little interference when I came in here, so it lifted a little bit. This is 4 hours, 44 minutes. Phase noise is minus 107. And amplitude noise is minus 102, means minus 157 dBc per hertz and minus 152 dBc per hertz. I switch on some infrared radiation to see what is the frequency shift that happens. There is an immediate phase shift that causes the interferometer to not be balanced anymore, and you can see the signal gets very strong. This becomes visible also if you look at the amplitude margin, which is going down. You can see now, right now, it is 20.5 dB on the first channel, but it changes rapidly. What we see is that the capacitance of a polypropylene capacitor changes rapidly while the temperature is changing. That is not what we want in an oscillator. So I have found now that polypropylene, while being reasonable for phase noise, is unreasonable for frequency stability. Here is a summary. There is no question that polystyrene is what I would like to use, but I would need high quality polystyrene. It has very low phase noise and amplitude noise. Before I temperature cycled it with infrared light, it was really bad. And I have seen previously there is a contact problem in these Chinese polystyrenes that I have access to. Silver mica, useless. The old mica, very unstable and completely useless. The ATC microwave capacitors were interesting, very low phase noise, but when changing temperature just very little, they started to produce noise. So these would be very difficult and had to sit in the thermostat. The other kind of ceramics inside glass had some noise, phase noise, and a little bit more amplitude noise. Polystyrene, interesting, but I think they have a contact problem because there is amplitude noise in those. And I don't have any other types. So I will try to heat treat the polystyrene to see if they become better. Here are polystyrene capacitors. The 4 ones in the group on the right side are heat treated in the oven at 150 degrees for half an hour, and you can see they have become very different. The one on the left here is untreated and looks very different. This procedure has changed the capacitance by about 10% upwards. They were 27, now they are about 30. But in this process I treated 9 and only 4 survived. The other ones became shortcuts. It's an interesting experience. I have treated 9 82 pF capacitors in the oven at 125 degrees nominally for half an hour. The physical change on them is much smaller. These ones are heat treated and these ones are not. I don't see any significant difference. They all have had higher pressure on the left hand side where some polystyrene has creeped out. But it's similar here and here. I will check them and then perhaps increase the temperature a little bit. I have measured all the capacitances. The first 9 have been in the oven. 2 of them are shorted, so something seems to have happened. Among the untreated ones, there are 2 that are very low in capacitance, 35 and 15 pF. And that's odd. When I compute the average of those that seem okay, I find 83.8 for the treated ones and 84.2 for the untreated ones. 7 of those, 10 of those, and I don't see a significant difference. The variation between the capacitors is fairly large, from 86 to 80 here, and from 86 to 82 here. So next step is to look at the series resistance of these ones. For this I use an high Q inductor to form a series link with these capacitors one by one, and then measure the impedance at resonance of this series link. This one is at 0.77 ohms or 0.76. It varies a little bit with the noise of the network analyzer. This one is nearly 3 ohms. It has not been heat treated like the previous one had. I can squeeze it a little bit like that, and that makes a big difference. Now it's 1.5 ohms. So it's obvious that there is a problem. Heat treatment helps. The ones that were in the oven, these ones are all near 0.7 ohms. The ones I have not treated, several of them are unstable and high in resistance, 2 ohms, 2 ohms, 4 ohms even. And only this one and that one seem reasonably good. Well, this also. But probably they are unstable. I will make a capacitor by making 3 of these in parallel to make the capacitance around 270 something. I had to increase the number of turns on the coil by 1 or 2, I don't remember, and I had to put some glue on it, and that degraded Q, and I think that's the main reason why Q is only 10 now. And of course I had to tweak the links a little bit also, but now I have a filter with similar characteristics as before, although slightly lower Q. And I will look at the sideband noise now. This did not work. One capacitor failed and became a short circuit. I have replaced it and try again. The voltage is rather high, so I think the polystyrene was too thin at some place. Loss. It's obvious the time or the temperature was too much for these capacitors. 3 have failed and I have only 4 left that still work. And I'm now running 3 of them to look at the phase noise and amplitude noise they provide. Something has happened in the device under test. The carrier is much stronger. I changed the tuning slightly. Well, I have to change the amplitude also. Now, it's pretty clear I have heated these capacitors too much. The phase noise is not very low, about -96. But the amplitude noise is lower, about -100. I don't understand quite what's going on. It seems to be a new process generating phase noise. Maybe places where the polystyrene is very thin, so the electrical field strength becomes very high locally. The filter response has changed drastically. I will retune it. I have retuned the filter. I don't know what the problem was, if it is the capacitors or whether it was the coil. But now it looks more normal. 6 decibels of loss and 12 for the Q. and 50 ohm at resonance. Across the capacitors I now have 30.5 volts. There are still stability problems. Something is drifting. Probably the coil. I used melt glue and that seems to be a bad idea. So I will replace the coil and see if things get better. The phase noise I see right now is minus 101, converts to minus 151 dBc per hertz. But since the carrier is about 1 dB stronger than desired, it means minus 150. And look at amplitude noise, it is very similar. This time I used this glue, ethyl polycyanacrylate. Very small quantities to fix the main coil, a drop here and a drop here. So there is very little glow as dielectric where there are strong electric fields. The links, there is no glow at all. I have just twisted them on each other to keep them steady on the coil. This filter gives me a Q of 18.7 with 5.6 dB loss, and the impedance is 49 ohms. The signal across the capacitors is 40 volts peak to peak. Stability is not restored and phase noise is very high now. You can see it here and also, of course, in the waterfalls. I reduced the signal level by 6 decibels. Well, I couldn't do that because the 6 dB step is noisy. So I have reduced the signal level by 10 decibels. The level is still unstable. And the sideband noise is very high, and it is amplitude noise mainly. The phase shift through this filter is fairly stable. It's the amplitude that is drifting. The system has been running overnight, 7 hours, at the reduced power, about 12.5 volts on the capacitors. After a restart and 1.5 hours of running, this is what I see. Minus 101 translates to minus 151 dBc per hertz, and it's still the reduced power. And this is the phase noise, and the amplitude noise is stronger. It's about minus 96. And I can look at both of them like this. And the carrier suppression is 50 decibels. I have restored full power. The phase noise is the same, but the signal-to-noise ratio of the measurement is very much better. You can see that the uncorrelated part and the correlated part are similar at the same level of minus 101 as before. That's the phase noise. And amplitude noise, well, minus 94. I don't know if this change is significant. The signal-to-noise ratio was fairly bad in the previous measurement. So, the capacitors are questionable. I will try some of the untreated, the best ones, in contact resistance, to see what they show in this setup. Just changing the copper slug position very little gave me the desired filter performance. 50 ohms, Q is 19, and the loss is minus 5.4 dB. The voltage across the capacitors is 42.0 now. The transmission through this filter is changing slowly. Here is the signal, which nominally should be at 59 millivolts. This is in about 1.5 hours. And I change in the interferometer on the amplitude. And then on the phase, and you see the phase change was very small, but there was a very large, well, very large, it's a couple of hundredths of a dB, like that. The phase noise is very low. Already after 3 minutes, I see something like minus 112 or so. It hasn't converged yet, it is only 30 averages. The amplitude noise is now about minus 87. It was minus 90 when I looked 1.5 hours ago. So there is a contact problem still, but not affecting the phase noise because the contact resistance is all the time low enough. So heat treating the way I did would destroy noise performance, although it fixed the contact problem. Now with 170 averages and 18 minutes, I see that the phase noise has increased. It's now around minus 107. And the amplitude noise is at 88. So there are stability problems with this, although the noise is fairly low all the time. Here I have a saturated solution of salt in water. Ordinary table salt, sodium chloride. And here are all the untreated capacitors. I placed them inside this container together with several nuts to make it not float. That was bad luck. I should have known better. Now I rinsed them in pure water a couple of times and hope that no salt has penetrated the capacitors. I have dried the capacitors in the oven at 70 degrees for about 10 minutes. They should be free of water now. The thermometer does not like the induction stove, so I switch it off. And it says 108 degrees. I don't know how accurate it might be. But according to the book, the temperature should be about 110, and the air pressure right now is 1015 hectopascal. I think that's about normal. I'm using this plastic container and I have verified that it survives this temperature. And I have arranged for it to not come into contact with the hot metal at the bottom of this cooker. It has been boiling like this for more than 1 hour now. This did not work well at all. Of those that I have treated, 2 of them became open, no contact. Some got a very high resistance, 14 ohms, 9 ohms and 13 ohms. And 1 became better, this one. I have placed heat shrinking tubes on the capacitors and I will give them 1 more hour in the boiling salt water. There is an obvious difference in the physical appearance of the capacitors. The shrink tube has worked. I have tested all my 82 PF capacitors of this kind. 4 of them were used before, 2 of them were okay. These 2 were very bad, 5 ohms and 2 ohms or so. And these are the ones I have played with in this video. Some I have destroyed by heating too much, and some were bad from the beginning. So I don't have many to use anymore. These are 300 PF capacitors. Old ones, I don't know where they come from. The smaller ones are rated 125 volts. The larger ones don't have any voltage rating on them. I had to remove several turns to get the resonance near 10 MHz. And here is the first capacitor I look at. It's one of the larger ones. And it comes at 0.2 ohms. I have measured 10 of each kind. They are all very good. There are some differences. This one 0.30, this one 0.18. These ones. I will look at the sideband noise to see if I can see any difference between them. I had to remove a couple of turns and to change the links a bit to get a suitable filter for sideband noise tasting again. Q is 22 and the loss 8 decibels. I can adjust that a little bit by different coupling at the two sides. Weaker coupling on the output provides higher loss and higher Q. There is 36 volts across the capacitor. To start, it was very good here, and then came a noise burst, fairly strong, and then a weaker, and now it has calmed down, and I have started measuring again. It hovers around -105 now. I will wait for a while. There are obvious noise problems. I can of course not be sure that it comes from the capacitor. I may have introduced some other problem, but I will try the other capacitor to see if it is different. Now I'm using the larger one that measured 0.3 ohms. It seems to be much better, no noise so far, and the level is in the order of -110, which is very good, and it's far from converged yet, although it goes in both ways. I think the situation here is the bigger capacitor has a thicker dielectric, and phase noise from polystyrene is related to the thickness of the dielectric. That explains what I saw when compressing the capacitors, that they lost performance. So higher voltage, precision, polystyrene. Where can I buy such things? The phase noise is -106, means -156 dBc per hertz. And the amplitude noise is -99, means -149 dBc per hertz. So this is a good capacitor, and it has been completely stable. I didn't adjust the amplitude for the latest 7 hours or so. When I increase the sensitivity of the color scale, I can see there are structures here. Here is a more quiet region, as well as here. But here it is significantly more noisy. So things are going on in the capacitor, but at very low levels. 3 times 100 pf polystyrene. Not very good. There are these. And if I look at the phase noise, it says -101. And the amplitude noise, -100. Another group of 100 pf polystyrene. These are very good. -110 for the phase noise and -101 for the amplitude noise. And amplitude noise and phase noise are fairly strongly correlated. I think these are the properties of the polystyrene and not the defects of the manufacture of the capacitor. So I would like to have this kind. I don't know how to get them. While waiting for quality capacitor with polystyrene dielectric, I am measuring those Chinese that I have, and here is one example. The green trace is the original measurement, and the yellow is after I heated 5 millimeters from the capacitor for about 1 second with the soldering iron. So this one has changed its capacitance and also the resistance, but that is not much, because the frequency the dominating part of the resistance is the coil, and that changes with frequency. Anyway, this one I classify as bad. Here is the next one. This one is bad. I cut the wire for it. This one, after heating, looks the same as before heating, so this is a good one. And this one is also okay. You can see the impedance. It goes something like that as a function of frequency. So I'm just looking for the change of the frequency. This is the procedure. First, solder far away from the capacitor, here and here, and then go to the network analyzer and press save trace. So then I have it there, yellow and green at the same place. And then the soldering iron. 1, 2, 1, 2. The frequency has not changed, so this one was fine. These are all 3 PF, and I use them in various numbers to set the frequency of my oscillators. Because tuning capacitors are always noisy because of contact resistance. These are all 3 PF, and I use them in various numbers to set the frequency of my oscillators. Because tuning capacitors are always noisy because of contact resistance. This one changed a little bit. I put it among questionable ones. But the next one is fine. This one has a lower capacitance and a higher series resistance. So it is not okay. Immediately after heating there are thermal effects. This one had a reduced capacitance, and now it comes back. And it all looks fine. This is one of those that I classify as questionable. The capacitance has increased a little bit, and the series resistance of the LC circuit has become maybe 1.5 or 2 ohms lower. So this is better now than it was before, or whether the sideband noise is affected or so, I don't know. So I put them aside and marked them in a specific way. I had 32 of these capacitors. 17 of them were fine according to this test. 6 of them were bad, and I have thrown them away. 9 I classified as questionable. They generally become a little bit better of the heat treatment, but there is some potential instability, I think. So I will leave it like that. The next size I have is 18 PF. 2 of them in series gives me 9 PF, and I can add 3 PF or 2 of them to step from 3 to 18 in steps of 3 PF with a reasonable number of components. This one changed significantly. It lost capacitance, although it seems that the resistance has become a little bit lower. So I consider this one uncertain and put it aside as a bad capacitor. Again, the heat treating. 1, 2, 1, 2, and the trays come back. Very small change, and I don't see the thermal effects either. So this one is good. I have tested 33 of these capacitors. 25 were fine. 6 of them useless, I have thrown them away. 2 questionable, I have marked them so I don't know which they are. 16 of these in parallel results in 299 or maybe 300 pf. I will use that in the interferometer and see what the sideband noise might be. This is now the device under test. And here is the filter characteristics. 50 ohms output impedance, Q 21.9 and loss 6 decibels. I don't know what the input impedance is, and that doesn't matter. This is not quite what I had expected. Noise is rather high. I can read about -99, means -149 dBc per hertz for the phase noise. And the amplitude noise is at the same level, as you can see here. I had expected 16 independent noise sources to sum up to something a little better than this. I'm testing all my capacitors of this kind. These ones are 39 pf. They are particularly bad, although those at 27 pf were all good. What I have here is what you can see, maybe. Well, right now I don't see any resonance at all. I touch it a little. Well, squeeze it. And there it is. And it was variable. As you can see, it still is. So, using this would be a very bad idea. I don't care to do a heat treatment. Maybe it would look better after that, but I don't trust it is going to be stable. So I just threw this one away also. Here is another one. The resonance is high above the desired, so the capacitance is very small. I tried to heat this one, and now the wires are in good contact with the aluminium foil. So I go back to the normal scale. And then it looks very good, but I don't trust it will remain good. So I reject it. The good ones look like this, before and after heat treatment. This one got lower losses after heat treatment. Not much, but it is a stability problem, perhaps. And I don't need a large quantity, so I just get rid of this one. A large number is like this. Well, now it disappeared. Touch it a little bit. And suddenly it makes contact. Maybe for a while, maybe. Another good one is still drifting slightly from the heating. 14 capacitors have survived this test. 25 go in the waste bin. Better capacitors have arrived. These ones are polystyrene from LCR, and the wires are welded to the foil. Here specifications. They come from here. I want to improve the sensitivity of the phase noise measurement, so I have connected this old mica capacitor 300 pf. Linrad and the PN2060 agree that the noise, the phase noise, is at about -81 dBc per hertz. This is with 40 decibels of carrier suppression, and they have been measuring during exactly the same time span here. The noise comes in bursts. I will now modify the resonance circuit to make the Q higher. This is the old resonator before I made any changes. Q is 22 and the loss is 5.7 dB. I have reduced the number of turns on the links from 3 down to 1 and connected 39 ohms in series with the output to make the interferometer still see 50 ohms, 49.82 as it turns out. Now, with this setup, I cannot measure the voltage on the coil easily anymore. I connect the oscilloscope probe, and of course the capacitance makes the frequency differ, so I have to compensate for that by tuning the screw. This has reduced Q a bit and increased the losses from 22.37 to 23.7. Well, the difference was not as big as I was assuming, so I can measure the voltage accepting that the error will be about 1.5 dB. So I do it the usual way, connect the oscilloscope probe and tune for maximum signal. Then I see 16 volts. Here is the phase noise with a modified resonator at 40 decibels of carrier suppression. It started with very strong noise and then it disappeared, and now it comes some regular mode. Now, of course, since the voltage is lower, the effect of the increased Q may not be so strong. But theoretically, higher Q should mean higher sensitivity to capacitance changes. And in an oscillator, the voltages will not be as high as I have had in previous tests. Not even as high as 16 volts that I'm using now. After about 1 hour, the noise was reasonably stable. So I started the long time measurement. This is 3 hours. And noise bursts come occasionally, as you can see up here. But the average over these 3 hours is minus 76.7 dBc per hertz. And Linrod and PN2060 agree on that. After about 1 hour, the noise was reasonably stable. So I started the long time measurement. This is 3 hours. And noise bursts come occasionally, as you can see up here. But the average over these 3 hours is minus 76.7 dBc per hertz. And Linrod and PN2060 agree on that. So with the 40 dB carrier suppression, I arrive at minus 116 for the phase noise and minus 122 for the amplitude noise. Now I have 2 of the 150 PF capacitors from LCR in parallel. Q is a little higher now, 49, and the loss a bit lower. So losses in mica are higher than the losses in polystyrene. And I didn't retune the links. The impedance is 49 ohms. So if I would adjust it, Q would go down a little bit and loss would go up a little bit. But I don't worry about those very small differences. So now I will look at the noise. But first the signal level, 17.0 volts. I had to change the color scale very much in order to see the noise in the waterfall graphs. And it's clear I see some noise. You can see the white regions, it's with the mica, it's much stronger. But this looks like some contact problem to me, what I see in the baseband graph. And I will wait for a while to get readings from the correlation spectra. Linrod is much faster than the PN2060 under these circumstances, the carrier is very weak. It's minus 28 dBm in the PN2060. The noise I see in Linrod is, if I try to make a smooth curve here, it is 97.5. And this, it has not converged yet by far, but it looks like it will be about the same. And the amplitude noise minus 102 means minus 142 dBc per hertz. These are the three 100 PF capacitors that had outstanding noise in the measurement with the previous coil configuration. I adjusted the coupling to get more precisely 50 ohms, and that changed, of course, the Q a little bit. But here is what I see: Q 48.8, loss 22.2, and 16.5 volts, because I'm loading a little bit harder on the coil. It's immediately clear that these ones are much better than the new ones from LCR. You can see in the baseband graph there is no noise close to the carrier like we had here. At wider separations they are the same, as you can see up here. So I will start the correlation measurements. It's clear this would take a very long time. I need more carrier suppression. With 50 decibels of carrier suppression, the carrier is very weak. 45 decibels below the nominal level in PN2060, and I cannot see the noise, the sideband noise. I just see the noise of the test system, which is at about minus 88 or so. In Linrod the situation is a little bit better. I can actually see now the noise, the phase noise at minus 104. But it has taken 1 hour, and the signal to noise ratio, distance from the yellow trace to the red dots, is rather small. So I have to reconfigure, put a smaller resistor at the output to get a higher signal level, because the noise floor is dominated entirely by the white noise of the receiver. You can see a flat noise floor here. The output resistor is now 24 ohms, and I have been a bit more careful loading the resonator approximately the same both from input and output. And now the Q is 35 and the loss 10 decibels. So I will get much more signal now. And I see 38.6 volts across the capacitor now. And in Linrod, the margin to saturation of the AD is 40 decibels. I will try with 40 decibels carrier suppression and see if I have better agreement then. Now, of course, the margin to saturation of the AD in Linrod is 10 decibels less, 30 decibels. And the level into PN2060 is 26 dB below what it should be. After 1.5 hours, I see minus 110 dBc per hertz in Linrod. That becomes minus 150 with 40 decibels carrier suppression. The previous measurement with 50 decibels, that gave me minus 147. So I think maybe this is the best setting. It is high enough above the noise of the Wenzel oscillator at minus 119, but there is not much margin. The PN2060 now gives minus 96, so I think that's an error of 4 dB due to the noise internally in the PN2060. The amplitude noise is a little bit higher, but at larger offsets it is significantly higher. So it doesn't have the same frequency dependence. And I read minus 109 here. I have reinstalled the two capacitors from LCR. The result is minus 99 dBc per Hertz in Linrad, and in PN2060 minus 95. The amplitude noise is significantly lower, minus 105.5. Those numbers are at 40 decibels of carrier suppression. The good capacitors, those that are 12 millimeters, measured minus 160 with the old configuration of the filter. The same capacitors now show minus 150. The amplitude noise, however, differs very little. It was minus 151, now it's minus 149. So I take that this is a better measurement, further from the noise of the test system. So it is reasonably reliable. When I then measure the LRC, it comes at minus 139, which is much more noise, while the amplitude noise is at minus 145. Here is the Hi-Fi Collective site on the internet, from where I bought these capacitors. And I used this tool and asked for polystyrene by LCR and used the filter function. And then I look at the 160, 150 PF here, and then more information here, and data sheet here. And here they tell me aluminium electrodes are used and terminal wires are welded to them to ensure satisfactory performance at low voltage and frequency. I will try to heat the leads of these capacitors 5 millimeters from the capacitor for about 2 seconds to see if the level changes. It is now 16.6 dBm minus, and if perhaps the noise changes. Of course, there is a big change immediately because the interferometer gets unbalanced. And I will wait for a while and then see how far away it has come. Now it seems the temperature has stabilized. I will change the frequency by tuning the slug on the coil for minimum to see if also the resistance has changed. The capacitance had decreased a bit. I had to increase the inductance of the coil. When doing so, I find that the resistive component has not changed much. The signal has changed by less than 1 decibel. Heating the wires 5 millimeters from the capacitor has degraded the phase noise by about 10 decibels. And now it is strong enough to give the same result in PN2060 as I have in Linrad. So previously, after a long time, I was reading phase noise 99 decibels. That's down here. And now I see something like, if I try to guess, 90. So 9 decibels. And I go for the amplitude noise. And that is 101. Or maybe 102. I haven't waited long enough, but it is a significant degradation, but not as big as for the phase noise. Previously I saw minus 105. So, well, I don't know what to say about this, but trying to improve them by heating seems to be a bad idea. 3 times 100 PF from LCR. Phase noise 103. Oops. I made some interference now. Actually, I saw 106.5 before I made that interference. The phase noise is minus 148 dBc per hertz. It will degrade because I made some noise when I come in here. And the amplitude noise is minus 148.5. Very much the same at 1 hertz. And now it has degraded because of this event. And I don't know the reason for that, if it is well, some acoustic noise. Yes. So vibrations in the air has to be avoided. The capacitors are hanging on thin wires. But I caught the performance before it was degraded. And it's much better than what I saw with the two 150 pf capacitors. I have glued the capacitors to the wall and to each other with ultraviolet hardening glue. So now they cannot vibrate individually anymore. And the strong noise you see on top here was while I was talking into the camera close to the unit. But now I'm sitting in front of the computer and do as before. Wow! And this seems much better now. So this was too far away to cause any problems. I have started a new measurement and it looks very good for the very first or second correlation spectra. We will see how it develops. And this is what I had to do to get this excellent performance. So I don't know if it stops air circulation or if it just makes sound level quieter inside here. I will continue to investigate these things, but I need to set a larger carrier suppression and accept longer measurement times. The phase noise now is minus 157 dBc per hertz, the best I have ever seen. It seems these capacitors are a bit microphonic, but that's no problem. So they are welded and are very good. The amplitude noise is much higher, minus 98 means minus 148 dBc per hertz, because I have 50 decibels of carrier suppression now. Here is the arrangement I have to get this result. First, this lightweight cat pillow, then protection to not touch the components, and then this is a one-sided PCB laminate glued to the metal, and on the epoxy side the two capacitors are glued onto the epoxy with UV hardening glue to get it immediately fixed. And that's it. This way the capacitors are protected from sound waves. I think they are microphonic. And they are not vibrating. Also they are fixed firmly to the box. I have placed 2 of the FSC capacitors inside a plastic tube and then filled the plastic tube with epoxy. The phase noise is about minus 154 dBc per hertz. Good, but not quite as good as with the 3 100 PF. These are 150. I will place the cat pillow on top to see if there is still any sensitivity to, I think it is infrasound, that is the culprit here. So now I have this thing back, so I know that there will be very little infrasound. There could be vibrations in the inductor, for example, or the capacitors could still have some sensitivity. The average noise was 106.25 or so here, and then I had some interference, so it went to 106.2, 106 something, and now it says minus 108, but that's only 15 averages. Now the phase noise is 106, means minus 156 dBc per hertz. It's a small improvement. The average has gone up by 2 decibels. So the main problem with noise comes from the capacitor being sensitive to infrasound. And now this little difference could be statistics, but probably it is the coil that is sensitive to infrasound to a small extent also. The amplitude is much stronger at minus 98, means minus 148 dBc per hertz. And amplitude and phase noise are not correlated in the region that is valid data from 0.8 to, well, the limit is 2.5. These capacitors arrived today in an envelope. I don't know from where they come, but I have bought on eBay from several different sources. Anyway, 150 PF, 630 volts, and I think these are FSC EX. And I mount them like this. It doesn't look good at all. I will leave it for a while because I see that the noise is decreasing. Maybe it goes down to a reasonable value within a reasonable time. The phase noise is very high, 137 dBc per hertz. I look for the amplitude noise, which is exactly the same. And correlation shows at 1 hertz they start to become similar, and above that it is the same modulation almost. These capacitors could be good microphones for infrasound, so I place this protection first and then the absorber for infrasound, like that. And it's immediately clear. It is much better now. So I will collect the new phase noise information. Now I use this ultraviolet hardening glue to modify the capacitors. A thin layer on it. And then UV light. And it's difficult to operate the camera at the same time, so this is a bad video. But you get the idea. I will do this more properly. Now there are fairly thick layers of this glue on both capacitors, and I hope it has hardened all the way so it doesn't change the pressure it might put on the windings inside these capacitors. I will see how these behave when I expose them to the infrasound. So now I run the sideband noise test with these modified capacitors. It's immediately clear that the sensitivity to infrasound is no longer a problem. The phase noise is minus 107 on the screen. I will put the cat pillow back on the unit to see if it goes down below the value I previously observed, which would indicate I have phase noise from the coil also, or that the cat pillow isn't really removing all the infrasound. The phase noise now comes at minus 164.5 at 1 Hz offset. It has still not converged well, although this is 1.5 hours. And this is close to the limit of what my system can do. The noise from the Wenzel oscillator that is added here is at minus 119. That's only 5 decibels, so it does contribute. The flat noise floor of my receiver at about minus 103. If I would increase the carrier suppression, the distance from the noise floor down to the noise I would like to measure would increase and make the adjustment of the interferometer extremely sensitive, because there is amplitude noise and it is stronger, and a small phase error will mix in amplitude noise with the phase noise. The amplitude noise is much stronger. Minus 99 on the scale means minus 149 dBc per Hertz. And amplitude noise is uncorrelated to the phase noise. And you can see the huge difference between amplitude and phase noise, which means the tuning of the interferometer extremely sensitive. So there may be a contribution from amplitude noise here. The improvement from 161 to 164.5 may be because the cat pillow is not removing all the infrasound, or maybe the coil is a little affected by infrasound. I cannot distinguish between those two possibilities, but I don't have to, because infrasound is not really a problem. I will use these capacitors in a sealed box, which is protected completely from infrasound. Now that I'm aware of the infrasound problem, I have a new look at these 3 old good capacitors when they are protected against infrasound. After about 1 hour, I see the phase noise at about minus 161 dBc per Hertz, maybe even 162. It's still rather noisy, because it is so far below the noise of my receiver at 102 or 103. So I would have to wait longer for this imaginary part to go down another 6 dB. But I'm not going to do that. I will be satisfied with this. Looking at the amplitude noise, it is much higher, minus 149. And here I can see that amplitude noise and phase noise are fairly strongly correlated. And I think maybe it's just because the carrier cancellation is not perfect, so there is a small phase shift. This is hard to investigate and not really important. It seems there are two solutions to the problem I have building good oscillators. I could use the welded tinned copper to aluminium, the FSC capacitors, or I could use capacitors with tin foil, and they are produced as FSCEX. They are also produced by some other company that doesn't answer the mail I sent to them, and I don't know how to buy them. But there are old capacitors with tin foil available on eBay, and I have not received any of them yet, but I expect them to be similar to what I have here, with noise levels below minus 160 dBc per hertz at 1 hertz offset, with the setup I'm using.